Hi, I'm Karimov, and today I will be presenting our joint work with Joël Vaknin and James Worrell on verification of linear dynamical systems. We consider discrete time linear dynamical systems which are given by a d-dimensional update matrix M and a starting point S. We are interested in algorithmically verifying properties of the orbit of such a system, which is the following sequence. The elements of this sequence are points in d-dimensional space, and each element is obtained from the preceding one through multiplication by the update matrix M. Let's look at an example. Here we have the three-dimensional dynamical system given by this particular update matrix M and the red starting point with coordinates 1, 1, and 5. The first few elements of the orbit will look like this. We can see that starting from S, our system spirals down towards the xy plane. Next, to see what kind of questions we might want to ask about our orbit, let us consider one situation in which such orbits arise. Suppose we have the following linear while loop with three rational variables x, y, and z. The initial values of these variables match the point S, and the numbers inside the loop come from the matrix M. Hence, the values of the variables x, y, and z after n iterations of the while loop correspond to the coordinates of the nth orange point on the left-hand side. Suppose we want to know whether this particular loop terminates. This corresponds to the question, does the orbit ever reach the region outside the green cylinder? In this particular case, again by simulating our orbit, we can see that this is indeed the case. Next, I'll describe a few other questions that we might want to ask about linear dynamical systems and the resulting decision problems. We begin with the point-to-point reachability problem, also known as the Cannon-Lipton orbit problem. It is the problem of determining whether the orbit ever reaches a given target point T. Equivalently, we have to decide whether the point T is in the orbit. For example, let us recall this dynamical system from before and select the point T to be the point with coordinates 1, 1, 2. We can see that the points of the orbit have z coordinates that become progressively smaller. And hence, after running the system for a few steps, we can conclude that presumably the green point will never be reached. Here's another example. Here the orbit spirals outwards from the origin. And similarly to the previous case, we can conclude that from certain point onwards, the points on the orbit will have distance to origin that is greater than the distance of the point T to the origin. And hence we can conclude that the green point is not in the orbit. Finally, here is another possibility. In this case, a tail of the orbit is dense in an ellipse, but the point T also happens to be on the same ellipse. In this case, it's very unclear whether the orbit ever reaches T. In fact, it does not. And the moral of this example is that not always we can find a visually obvious and a metric way to argue non-reachability. Well, in spite of this, the orbit problem turns out to be decidable. The problem was posed in 1969, and in 1980, Cannon and Lipton gave an algorithm that remarkably works in all dimensions. They later showed that the problem can in fact be decided in polynomial time. You can read more about the history of the orbit problem in Richard Lipton's blog. But with respect to our story, the orbit problem marks a beginning. And next we'll consider what happens when we generalize the target set from a single point to various geometric sets. The first generalization we consider is from a single target point to a target hyperplane. For example, suppose we are given a three-dimensional dynamical system and a plane H. The configuration might look as follows. Now we ask, does the orbit of our dynamical system ever reach the green region? By simulating our system for a few steps, we can confirm that this is indeed the case. In the general version of the problem, we are given a d-dimensional dynamical system and the target hyperplane H. And the question is, just like before, to determine whether the orbit of this dynamical system has an element that is in H. Since H is precisely the set of all points whose inner product with the coefficient vector C equals V, the hyperplane reachability problem is equivalent to the problem of determining if the following sequence ever equals. This sequence, however, turns out to be a linear recurrence sequence. And as a result, the hyperplane reachability problem is equivalent to the famous Skolem problem. The Skolem problem is simply the following. Given a linear recurrence sequence with integer coefficients, determine whether it is ever zero. The Skolem problem has been open for almost a century now, and currently we only know decidability in dimensions at most 4. What this means for hyperplane reachability problem is that we should expect to solve it in dimensions at most 3. 3 and not 4 because the Skolem problem in dimension D is equivalent to the hyperplane reachability problem in dimension D-1. An alternative family of simple target shapes to consider would be the set of all half spaces. A half space is basically what is on one side of a hyperplane. Using the same analysis that we did for the hyperplane reachability problem, we can show that the half space reachability problem is equivalent to the positivity problem, which is the following. Given an integer linear recurrence sequence, determine whether all the terms are positive. Just like the Skolem problem, the positivity problem is open and is known to be decidable only in low dimensions. Moreover, the positivity problem is thought to be harder than the Skolem problem. The Skolem problem can be reduced to the positivity problem, but in addition, the positivity problem is hard with respect to certain open problems in Diophantine approximation. The morale is that there are significant obstacles to model checking even reachability properties of dynamical systems in arbitrary dimensions. Despite the hardness results that we just described, there are encouraging results at lower dimensions. Now we consider the polytope reachability problem. For our purposes, a polytope is any set that can be obtained from half spaces using finitely many intersections and unions. For example, in 3 dimensions, polytopes include all the polyhedra, but also unbounded and lower dimensional shapes. For example, by intersecting 2 half spaces, we can obtain a plane, and by intersecting a plane with polyhedra, we can obtain polygons. The polytope reachability problem turns out to be decidable in dimensions at most 3, and in dimension 4, it is hard in the following sense. Decidability or undecidability of the polytope reachability problem in dimension 4 would of course resolve the Skolem problem in dimension 5 and tell us something about approximability of Lagrange constants of a certain class of numbers. This is the Diophantine hardness result that I referred previously. Okay, so we've been talking about reachability problems for a while now, but reachability questions constitute only a very restrictive fragment of what we might want to know about an orbit. In particular, we would like to know how to answer queries about orbits that refer to some kind of an infinite behavior. For example, we might want to find out if the orbit eventually gets trapped in a particular set, or if it always visits a particular set immediately after visiting another set. To be able to answer such questions, we studied the problem of model checking linear temporal logic on orbits of linear dynamical systems. In order to be able to state our result in full detail, we will need one final concept. Recall our linear loop in 3 variables and the corresponding reachability problem from before. The issue here is that neither the green cylinder nor its complement are actually polytopes. In fact, already in the context of linear while loops, the guards of the loop will often contain arbitrary arithmetic expressions in the variables, not just the ones that result in polytopic targets. As a result, many interesting and natural sets are not polytopic, and we have to generalize. The generalization is to the class of semi-algebraic sets. A semi-algebraic set in D-dimensional space is defined by a Boolean combination of equalities and inequalities involving polynomials in D variables. For example, let P and Q be the polynomials in 3 variables defined as follows. We obtain that the set of all points that satisfy these conditions is given by the orange surface. If we change the requirement that p of x, y, z is equal to 0 to p of x, y, z is at most 0, the set that we define is the orange surface and everything beneath it. Semi-algebraic sets constitute a large class. In fact, the classical result of Tarski states that semi-algebraic sets are precisely those that are definable in first-order theory of real numbers with addition and multiplication. From now on, we will allow our target sets to be arbitrary semi-algebraic sets. Since semi-algebraic sets are closed under intersections, unions, and complements, it's convenient to consider semi-algebraic partitions of the ambient space. In this example, we have partitioned the three-dimensional space into a torus, an ellipsoid, a bowl, and an outside region, all four of which are semi-algebraic sets. Now let us add an orbit to the picture. Because we have a partition, at each step our orbit will be precisely in one of the semi-algebraic sets. By writing down the set corresponding to each point in the orbit, we obtain an infinite word over the target sets that records all the relevant information about the behavior of our orbit. Once we have this word, the next step is to ask questions about it, and for this purpose we will be using formulas of linear temporal logic. Linear temporal logic augments the classical propositional logic with temporal operators. For example, the formula diamond T is equivalent to the statement the orbit is eventually in the set T, which is the classical reachability property that we've encountered many times already. But the point is, by combining and nesting various temporal operators, we are able to express properties that are much richer than just reachability. For example, the formula box diamond B states that it is always the case that the orbit eventually enters the bowl. Or equivalently, the orbit enters the bowl infinitely often. Another example, this formula states that whenever we enter the bowl, we stay there for at least another step before leaving for the torus. Once we have agreed on the language for expressing the properties of our orbits, the problem is now the following. Given a linear dynamical system, a semi-algebraic partition, and an LTL formula over the sets appearing in the partition, decide whether the orbit satisfies the LTL formula. We show that this problem is indeed decidable in dimensions up to 3. In dimension 4, we of course inherit the hardness result for polytopic reachability. The key concept behind our algorithm is the structure of the characteristic word of the orbit on a semi-algebraic set. This characteristic word is over a 2-letter alphabet and has the letter plus at positions that correspond to elements of the orbit that are in set S and minus at all other positions. This set has the following structure. Excluding a certain prefix, the remainder of it can be generated as follows. Start at point 1, 0 on the unit circle, and at each step multiply the current vector by a fixed unit vector. This corresponds to rotation through a fixed angle. Every time the vector is in a certain interval, add plus to the word, and every time it is not, add minus. The suffix we obtain this way is not semilinear, but it does have a kind of periodic behavior. The significance of this for our decision procedure is as follows. Also, all kinds of behaviors that our orbit will eventually demonstrate with respect to certain semi-algebraic sets will take place within a certain number of steps. Because in this unit circle, everything that can happen will happen within a certain number of steps. Hence, our algorithm is quite simple. We first estimate the number of steps we need to run our orbit for, and then check this prefix for evidence that the orbit does or does not satisfy the LTL formula. The magnitude of the prefix that we need to compute depends on the algebraic numbers that define this rotation and the intervals. In conclusion, we have studied decision problems about orbits of linear dynamical systems and showed how to model check three-dimensional orbits against LTL formulas of semi-algebraic sets. At higher dimensions, we run into the Diophantine and Skolem hardness results that are already known for polytopic reachability. One problem that remains open now is the following. Suppose, in addition to generalizing the target sets, we want to generalize the starting set. For example, we might want to know whether all orbits starting from a given semi-algebraic set satisfy a particular LTL formula. It seems like solving this problem will require new ideas. This was all I wanted to say. Thank you very much.